So in this section, our ultimate goal is to derive the radial component of the solution to the time-independent Schrodinger equation. And then in order to derive this, we've defined the function u of r, so u is a function of r, and then u of r is going to be equal to r times the radial component. And then we know that this function u must satisfy this differential equation. So if we manage to solve this differential equation, we can just divide it by r, and then we would have obtained our radial component, and that would allow us to construct the solution to the time-independent Schrodinger equation. So now we will turn our focus onto solving this differential equation. And so first of all, you can see that there are a lot of terms in this differential equation, so we're going to simplify this first. So the first thing we're going to do is that we're going to divide both sides by the energy level E. So note that we're going to consider the cases when the energy level E is smaller than 0, so this would correspond to the bound states. And then first thing that we're going to do is that we're going to divide both sides by the energy level E. And so this is what we're going to get. So plus h bar squared divided by 2me L plus 1 divided by r squared, u is equal to u. And then the next thing we're going to do is that we're going to define a new symbol k to be equal to the square root of negative 2me divided by h bar. So note that e is a negative number, and then that's why we have a negative sign here to make this whole term positive overall, and then we can apply the square root. So applying this symbol, we can further simplify this differential equation. So you can see that first of all, this term is equal to 1 over k squared. So let's open a new page. So we have 1 over k squared d squared u dr squared. And then for this next term, I'm going to multiply the denominator by 2m, and then multiply the numerator by h bar squared. And then I'm going to compensate for these two extra terms by multiplying the numerator by 2m, and then the denominator by h bar squared. And then if I put the negative sign over here, you can see that this is actually also 1 over k squared. So we can also simplify this over here. The 2 and 4, they cancel out. So in the end, what we get here is me squared divided by 2 pi epsilon h bar squared, and then we also have an r, and then we have 1 over k squared. And then for the next term here, you can see that this is equal to negative 1 over k squared, so don't forget the negative sign. So we have negative 1 over k squared L plus 1 divided by r squared. And then we are going to multiply this by u is equal to u. And then now one thing I'm going to do is that I'm going to group some of the terms together. You can see that there's a k squared r squared over here. I'm going to group them together as kr squared. And then here you see that we have k squared and a r. So I'm going to put one of the k's here at the bottom, and then I'm going to group the kr's together. And the reason I'm doing this is because I'm going to define a new symbol called y to be equal to kr. So in the book, Griffiths uses the symbol rho, the Greek letter rho, to represent kr, but I'm not very good at drawing Greek letters, so I prefer using y instead. And then I'm also going to define another term, y naught, to be equal to these terms over here. So y naught is going to be equal to me squared divided by 2 pi epsilon h bar squared times k. And so with these definitions over here, we can further simplify this differential equation. So this first term here, this becomes d squared u dy squared. So the reason why this becomes d squared u dy squared, actually I can explain this. So first of all, just consider the term du dy. And then if I'm trying to evaluate this, I can use the chain rule. So this is equal to du dr times dr dy. And then dr dy in this case, you can see that, so du dr dy is equal to 1 over k. So you can just differentiate both sides, and you'll see that it is equal to 1 over k. And then if I differentiate both sides again, I get d squared u dy squared. And this is equal to applying d dy to this expression. And then once again, I'm going to use the chain rule, so this becomes d dr, du dr 1 over k, and then we have dr dy. And then once again, dr dy is equal to 1 over k, and then it combines with this 1 over k. So this 1 over k is unaffected by the dr, so in the end you have d squared u dr squared, and then you have 1 over k, and then you have another 1 over k, so 1 over k squared. So you can see that d squared u dr squared 1 over k squared, which is exactly this term, is equal to d squared u dy squared. And so that is why we can now simplify this differential equation by rewriting this term as d squared u dy squared. And then here you get all these constants. This is just y naught, and then divided by kr, which is just y. And then here we have negative l plus 1 divided by, in this case, y squared, and then multiply u is equal to u. And then we can now rearrange this slightly. So I'm just going to dump the terms to the left-hand side. So we know that d squared u dy squared is equal to, first of all, 1 minus y naught divided by y, and then plus l times l plus 1 divided by y squared times u, where in this case y is equal to kr, y naught is equal to me squared divided by 2 pi epsilon h bar squared k, and where k is equal to the square root of negative 2me divided by h bar. And so I'm going to stop this video here at this point. So far we have managed to simplify our differential equation into something that looks rather nice. And then in the coming videos we will continue to tackle this expression here, and then ultimately we would obtain the function u, which would give us the final solution to the time-independent Schrodinger equation.